Hey everyone, thank you to the organizers for putting this together. It's great to be here in person. The title of my talk was To Be Determined because my student Nick and I were trying to finish up this work with the title Eigenstate Pre-Thermalization Hypothesis, if that intrigues you. Unfortunately, that's not quite yet ready for prime time, but we'd be happy to talk to you about that informally. Instead, I'm going to tell you some things we've been thinking of on non-unitary dynamics. This is in collaboration with two postdocs at Stanford, Mateo Polity and Tibor Rakovsky, who are both in the audience. There may be some things overlapping with Mateo's talk from a couple of weeks ago, but I'll try to give a slightly different perspective in the beginning. Okay, so this conference is very timely, and we've heard many interesting things about non-equilibrium universality in many body systems, ranging from quantum thermalization, foundations of stat mech, chaos, hydrodynamics, new types of dynamical phases in universality classes, new order parameters, well beyond correlation functions, think of entanglement dynamics, complexity, and what have you. Indeed, there's been lots of interesting work on all of these topics over the last decade or so, but much of it, at least in the many body setting, has been in the context of unitary time evolution, right? But unitary evolution is, of course, only one half of the most general way to describe quantum mechanical evolutions of systems, which, in general include both unitary evolution and non-unitary measurements, which may fully or partially collapse the wave function, right? And especially in the NISQ era that we supposedly live in, right? So in this age of NISQ experiments, the noise part of that brings in non-unitarity in an essential way. So in these experiments, you both have uncontrolled noise in terms of, just dissipation or decoherence from some environment, but you also have more controlled forms of non-unitarity in the form of measurements, okay? So in general, thinking about non-unitary and many body systems is very timely, very important. And of course, there is a large body of work on non-unitary systems in various fields like quantum optics and others, but much of that is still in the few body limit. So as a community, we're only now starting in the last few years to think seriously about non-unitary many body systems. And, as we heard from Ehud's talk and Sebastian's talk, a lot of interesting work in this regard was started by this set of papers by Matthew, Adam Nahum, and others, where you think about monitored quantum circuits. Okay, so in these circuits, the observer who's making the measurements is playing quite an active role, okay, because this is the physics of individual quantum trajectories. So you can imagine a system that's evolving with some unitary evolution, being subject to measurements at some rate. And then the idea is to follow specific or individual quantum trajectories corresponding to specific sequences of measurement outcomes. So this observer is keeping track of everything that the observer measured, right? And in this setting, the wave function evolves at a pure state, which is constantly projected into the appropriate measurement outcome. And this is in contrast with the kind of more familiar setting of open systems, where the bath or the observer is more passive, and all the results of these measurement outcomes are lost or averaged over. So then, your system evolves as a mixed state, right? So actually, this dichotomy often reminds me of my childhood, where I went to a very strict girls' school, which is common in India, and there we had people who were actually called monitors. And their job was to keep track of all of us and make sure we were not 5 minutes late, or our hair was not an inch too long, or our skirt wasn't an inch too short. So they did our best to keep us misdemeanor-free and pure, while the boys' school across the street was much more rowdy and fun. But anyway, okay. So, all right. So in this setting of trajectories and following and looking at properties of individual trajectories and then averaging over ensembles of these trajectories, there's this entanglement phase transition, which we've heard a lot about, where if you're making measurements at some rate p, if that rate is small enough, you can get an entangling volume law phase. whereas at pretty high rates, you get a disentangled area law phase. So this is referring to the spatial entanglement properties of the late time states that are of the late time trajectories. Okay, so there are many interesting things about this phase diagram. There's questions about the area law phase, its interplay with order, which Matteo talked quite a bit about. There's lots of work on this transition, which numerically appears to look like a CFT, and there's lots of work trying to understand the properties of that CFT. And there's also this volume law phase is also extremely interesting in its own right. And we heard about this a little bit from Ehud. The way that we think about this now is as a dynamically generated error correcting code, where the unitary part of the evolution scrambles the quantum information in very, very non-local degrees of freedom or non-local logical qubits, so that the local measurements are not able to disentangle the system. Okay, and in this view of this phase as a dynamically generating error corrected code, this subleading correction here. So notice that the volume law, I'm thinking in a system of 1D. So I have this volume law scaling with some entropy density S, but there's also this subleading logarithmic correction. Okay, and that may not seem like much, but it's actually one of the most interesting features about this phase. It's what makes this into a non-thermal volume law phase. Okay, so volume law may lead you to think it's just boring. Thermal states are volume law. Why should I care about volume law states? Usually we all care about area law states and thinking about patterns of order in these. But actually this is a very special type of volume law. It's a non-thermal volume law. And this subleading correction is key to the robustness of this phase against measurements. Okay, and if this correction was not present, you can in fact prove that if you made a finite density of measurements and kept doing that, you would disentangle your phase. Okay? So understanding the nature of this non-thermal volume law and the origins of this logarithmic correction, those are really important questions that people are thinking about. Okay, and then I should say here that if you have this kind of more passive observer, this setting with the bath where all the outcomes are averaged over or thrown away, then you don't get this kind of entanglement phase transition. But of course, there's another body of work where maybe by adding in some kind of drive, or you can get qualitatively different types of maybe driven dissipative phases and so on. Okay, but that's a totally different setting. Good. So let me walk through how even though these two settings may seem very different, there are certain classes of circuits and certain settings in which it's actually very useful, where these end up being connected, and it's actually very useful to try to exploit that connection. Okay, so I'll start with a very simple model. Okay, so you have a semi-infinite chain subject to some kind of boundary decoherence. Okay, so you can just think of this large chain which is in contact with some huge bath at one end. Okay, and now you can ask that without this bath, the state is a pure state. Okay, so its entropy of the state as a whole is 0, and you can ask what the entanglement of the mixed state is as a result of this boundary dissipation. Okay, so the entanglement of this mixed state, you can visualize it in some sense as a spreading, as coming from the spreading of decoherence from the boundary into the bulk. Okay, so if you had a very simple, so this is naively a very simple problem, and you would think that if we know how operators spread in the bulk, or we know the dynamics of the bulk, then this is pretty simple. And for instance, if you had something that was thermalizing, if you had just like random gates here which spread entanglement and operators and all of that ballistically, you would think that if you put a boundary channel there, boundary decoherent channel, then this decoherence would also spread ballistically, and you would have the entropy of this mixed state grow in time with some velocity v. Okay, and indeed that expectation is correct, and it happens to be the leading order answer. But even for this very simple, like featureless problem of just random unitary gates and boundary decoherence, you actually end up getting this interesting logarithmic correction in this problem. Okay, and I'll explain where that comes from, and this ends up being deeply connected to this log correction for the stability of the volume law phase that I told you about earlier. Okay, so all right, so this is one familiar picture. Now let's take this view that, you know, we have all of this dissipation at the boundary, but what if you don't want to throw all that information away? Okay, let's make our observer more active. So instead of throwing all this information away, let's collect it. Okay, so the simplest way you can do that is take the qubits that live at the boundary and let's just put them in different ancillary qubits. Okay, so we have some ancillary qubits in this subregion A. You can use a bunch of swap gates to just take whichever qubits lived at the boundary here and swap them into living in this kind of space-like region A over there. Okay, so far I haven't done anything. If you want to recover this picture, you just have to trace over that subregion A and throw away all your information. Okay, but you don't have to do that. You can now choose to look at it in different ways, and you can gain information about your system by accessing that information. Okay, so if I was trying to make an analogy with high energy physics, I would say that, you know, my system is like a black hole and it's emitting Hawking radiation, and I can either choose to discard that radiation, or I can actually look at that emitted light, collect that information, and indeed the entropy, the entanglement entropy of that emitted light with my system also has this interesting structure and this interesting law correction. Okay, so it's not featureless. Okay, good. Now in the next step, you know, so the observer has collected this information. So far not much has happened, but now I can start doing measurements to make interesting states. Okay, so the information that was collected already had interesting entanglement structures with B, but now I can go in and I can make projective measurements, for instance, on B. That's what I've done in this top layer, where those qubits that you know, if I want to make a state only on A, I can either trace out what lives on B or project out what lives on B. So here I'm projecting out what lives on B to create this state on A. So far, I guess you don't have much reason to expect it to be very interesting. I'll show you it can be interesting. But so far what I've done is I've made a potentially interesting state on A. And now, for the last step, I can rewind these qubits back, put them at the end of this circuit here, because these are just swap gates. Okay, they're just moving information from the edge to the top. So now I have this state that lives at the output of this sideways evolution. Okay, and this is the only slide in which I'm going to draw the sideways evolution explicitly. If I have these yellow boxes, they mean unitary gates, and the caret denotes the direction of unitary time. But what I'll show you is that, you know, if you view these unitary gates sideways, generically each of these boxes, when viewed in this sideways direction, is a non-unitary operation, and specifically it's a monitored type of non-unitary operation because it corresponds to a specific deterministic outcome. Okay, so it's like an individual post-selected trajectory of non-unitary evolution. Okay, so what we've done in this circle is taken individual post-selected trajectories of non-unitary monitored evolutions and related them to this problem of unitary evolution with boundary decoherence. Okay, so what does this get us? First, it actually gives us a great degree of analytical tractability for this class of monitored dynamics. Okay, a lot of our progress in understanding these questions has come from numerics on Clifford circuits, or in mappings to certain stat-mech models or mean field models, which operate in various large Q limits or all-to-all limits. But here we have an explicit microscopic evolution. There's no limits, there's no coarse graining, and you know, depending on the unitary gates we pick, you know, this is a problem, unitary gates plus boundary decoherence, that we can actually understand in a lot of detail. Okay, so we gain this degree of analytic tractability. Second, we either greatly ameliorate or eliminate, depending on the question we're after, this kind of measurement post-selection problem for experimentally realizing these classes of non-unitary monitored circuits. Okay, so the experimental challenge is, if this entanglement transition is only visible after post-selection, so you pick a certain outcome, a certain sequence of measurement outcomes, you get some output state. But to measure anything, you have to prepare that same output state over and over again, okay, which means replicating that same sequence of measurement outcomes over and over again, which has an exponential cost in the space-time volume, okay? Instead, what this kind of prescription allows you to do is prepare these kinds of interesting output states of monitored evolutions with a vanishing density of measurements, measurements that only live at the end of time. Okay, so this helps us with this measurement post-selection problem experimentally, and much more broadly, the perspective that I want to present is, we should not just be, a lot of our effort in many-body physics used to be, what are the interesting classes of ground states we can get? Okay, so we can get ground states with different kinds of order, different kinds of topological order, and so on. But now I think the broader question to ask is, what are all the different types of many-body states that we can get, which are obtainable using the ingredients that we now have at our disposal, which could be, unitary dynamics quite generally, plus these ancillas or different ancilla qubits that could be used as a resource. And you could use those ancillas as a resource to selectively store or manipulate or measure different bits of quantum information. Okay, so like in this picture, I use these ancilla qubits, they collected some information, maybe I make some measurements, maybe I throw away that information. But using this larger toolkit of unitary evolution plus selective measurement, storage, and collection, what are all the, can I get new types of many-body states, okay? And indeed, while I was focusing on this volume law phase and the law correction, one of the upshots of our work is that indeed, by looking at different types of unitary dynamics and then viewing them sideways and taking this perspective of ancillas, we can get different types of states that don't generically occur when you're thinking of just equilibrium physics or even non-equilibrium unitary physics. In particular, you can get, fractally entangled states is one example of something we presented. But I think this broader question is very much open, and I think there's lots of interesting work to be done there. And I want to flag just, one recent paper from the Honeywell group that did something along these lines. So what their goal was to prepare or sample from a 1D MPS, matrix product state, okay? And they considered a certain specific class of MPSs which had bond dimension 2, so just very, very small entanglement, okay? And that's your picture of the MPS, those are your qubits, those are your, so it's nominally in an infinitely large system. And now you can do this isometry transformation between these MPSs and these unitary operators. And then, you can take this state, and what you can end up doing is, you can convert this space, this MPS which lives in space, into a sequence of measurements in time. Okay, much like we were switching between space and time fluidly in the last slide. So in particular, once you've made this unitary, the point is that, the sigma, you can measure it, because it never, once you've made this state here, it never re-enters or feeds forward into anything that happens later. So you can measure that qubit out, reinitialize it, act with it on you, measure it out, reinitialize it. So then you can sample from this MPS, which lives in an infinitely large space, by using only 2 qubits. Okay, there's a qubit that you're using as this register here, and then there's a qubit which is carrying your entanglement, and it's only 2 because they limit it to low bond dimension. If you wanted higher bond dimension, you'd add more qubits up there. Okay, so again, by just looking at this in time, you're sampling from this state in space. Okay, but this is just an example of bringing in ancillas, measurement records, storage, measurement, reinitialization into our toolkit of things we can do to make interesting many-body states. Good. Any questions? Yeah.
I assume that your unitary that you would apply would depend on the outcome of the measurement in order to create the state that you desire?
No, the unitary just depends on what this MPS happens to be, because that's an exact mapping. So you just put that in there, and it's a very interesting question to ask about that kind of interactive dynamics where you want to later act with unitaries depending on what you measure. But in this case, because it doesn't depend on what you measured, it allows you to just keep reinitializing and using that qubit.
Okay, so that's because they're trying to sample as opposed to create a desired state, right?
Right.
Thank you.
Yeah. Well, they're creating this MPS, but then if you measure it out, it's like measuring out these qubits here, right? It's like it's sampling from it, because each time you make a measurement, you'll get some bit string, right? So it's like projecting a bit string onto the actual MPS, and that's the sampling. Yeah. Okay. So now let me step back and drill into a few more details about this mapping that I was telling you about. Okay. So we have we have gates. These gates are unitary in the time-like direction. So you have these two input qubits, I1 and I2. They give you two output qubits, O1 and O2. That's a unitary matrix. When we're doing this kind of sideways evolution, we're going to view the matrix, from left to right instead of up to down. So then those are my inputs, and these are my outputs. Okay, this gives me a different object, U-twiddle, and generically, this U-twiddle is going to be non-unitary. Okay. There are, of course, special classes of unitaries where a unitary viewed sideways is also unitary. These are these dual unitary models that Tomasz Prosen talked about and that have been very useful when thinking about chaos. Okay, but generically, this is going to be non-unitary. As a very simple example, if you start with the identity, drawn this way, it looks like two world lines going from the past to the future, but then when viewed on its side, this ends up being a specific projective measurement onto this up plus down bell state. Okay, and the key here is that because you started with a specific unitary operator, when viewed on its side, it is a specific projector onto a specific bell state. Okay, it's a deterministic projector. There's no randomness there, right? So the example that I gave you was a projective measurement, but in general, you can get weak measurements, but even then you're going to sample from a specific element of your POVM set. And the idea is that these are always forced, there's always the same outcome. So we can use this to simulate the effect of post-selected measurements without the randomness. Okay, and that's the upshot. That's how it helps you with this post-selection problem. Okay, so this is just a list of references to show that this kind of sideways evolution has also proved very useful in the unitary context by giving us insight into many different problems. But here I want to view the sideways evolution as a non-unitary evolution in its own right. Okay, good. So the question that we'll be after is the entanglement scaling in these space-time dual circuits. So generally you have some input state coming in from the left and some output state on the right. These tildes denote the dual evolution. So after some time t tilde, say you want to know the entropy of some subsystem A, which lives on a space-like slice of this output state, or I guess this is, yeah, that's right. We wait long enough in the dual direction that we assume that this has saturated to what it's going to be. Okay, and I could prepare whichever input state I want most generally, but it's convenient to prepare this kind of bell pair input state, which in the forward time direction just looks like open boundary conditions. Okay, so when you want to implement these things in the lab, it's convenient to start with this specific input state, because in the lab you don't have access to these dualized gates, you have access to these unitary measurements, which you're then going to use to create these output states and then teleport them and view them in certain ways. Okay. So the question is, what's the entropy of that subregion A? Okay, and the point is that in this limit, that the rest of the system has gone off to infinity. Okay, so if you have this infinitely large dual system, and you want the entropy of some subregion, which could itself be very large, all the information that crosses this cut B, okay, gets isometrically encoded in A bar. Okay, so this you can prove, it's in our appendix. So then the problem of calculating the entropy between A and A bar ends up being reduced to the problem of calculating the entropy between A and B. So this huge part of the circuit can just be elided away. Okay, so now you're left with this much smaller circuit. It has spatial extent L tilde. It's evolved in dual time for time T tilde, and you want to know the entropy between A and B there. But, you know, this state on AB, as written here, is a pure state. So to get the entropy of A, you have the choice of either tracing out A or tracing out B. Those are equivalent. And it's convenient to trace out A instead, okay? And this act of tracing this A out, in fact, looks like this fully depolarizing erasure channel, okay? So that's where this decoherence came from. And once you've put it all together, this gives us this key relation that I had flagged at the beginning of my talk, that in order to get the entropy of this subsystem evolving under dual evolution for time T tilde, you can relate it to the entropy of a mixed state. That's what this decoherence looks like. The entropy of a mixed state evolving under unitary evolution, but subject to boundary decoherence. Okay, so that's this connection between unitary plus boundary decoherence and output states of dual monitored circuits. And this allows us to now make a whole bunch of analytic predictions, but more importantly, because we know that we can have all sorts of classes of different unitary evolutions, it allows us to get many different flavors of different output states and different types of scalings that go beyond just area volume log, okay? But let me quickly work out the familiar case first of just a chaotic circuit, okay? Okay, thanks. So a very helpful toy model is, suppose you want a chaotic circuit, you just act with Haar random unitary gates subject to boundary decoherence, and you want to ask what's the entropy of the mixed state in that setting. Okay, so we can start with the baseline problem. This is no boundary decoherence, but you have this Haar random circuit, and you want to know the entropy of some subsystem A. This can be worked out exactly, or at least the average purity, which is related to the second Rayleigh entropy, can be worked out exactly. This was done in this set of papers here. And the idea is that you want to look at trace of rho squared. So you have 4 copies of your state, okay? And this gray box, basically the 4 copies is because rho is 2 copies, it's psi, rho squared is 4 copies. This gray box is a Haar average over those 4 copies, okay? And then because you have trace, the whole rho A is a trace over B, the rest of the trace is the trace over the rest. So depending on whether you're an A or A bar, the top of your evolution, this may look familiar from Ehud's talk, either the 4 copies will either connect in this loop structure or that loop structure. That can be mapped to these kinds of effective Ising-like variables, okay? And then you can map the calculation of this purity to a random walk problem in this circuit, okay? So you start there, and at every step, your random walker either goes to the left or the right. And if you put all of that together, you get that your entanglement entropy grows ballistically in time with a velocity that depends on the local Hilbert space dimension. Okay, but this is not working in any large Q limit. This can be done for any Q. Okay, so the related problem that we want to solve is that of random unitary gates subject to boundary decoherence. Okay, so this part of the circuit looks exactly the same, and the boundary decoherence, so now you want the entropy of this whole state, and if you didn't have this boundary decoherence, it would be 0 because it would be pure, and this difference in boundary conditions is now only acting, or is only starting at the edge. Okay, now what ends up happening is that, again, you have this random walker, but if it's taking a step at the edge, then it does what it used to do before. But now if it takes a step towards this boundary, it has some chance of being absorbed by that boundary. Okay, so this is like solving this domain war problem, but subject to this partially absorbing boundary condition. This is a problem that has been solved in various StatMech textbooks, and it can be mapped to the random walk survival probability of this domain wall, which gives you this extra factor of square root of t, which when you look at the entropy gives you this logarithmic correction. Okay, so that's how, in this very microscopic sense, you can derive this log correction here, and that's the non-thermal piece that I had alluded to earlier, and this entanglement velocity in the unitary evolution ends up mapping to the entropy density under the space-time rotation. Okay, so I'll just say a few technical things, which is we got this 1/2 log correction when this subsystem lived on the edge, but actually if it lives in the bulk, then you get this 3/2 log correction. And this is the same log correction that's predicted to exist in the usual hybrid unitary measurement circuits. It also agrees with this kind of coarse-grained capillary wave theory picture of this phase that Matthew and Yaodong put together. And in fact, you can look at other features, not just the entropy, but you can also look at how the mutual information of a qubit inside some region A scales with the outside. Okay, and that again in this very recent paper was predicted to go scale down with system sizes x to the minus 1.25. For this exponent to be bigger than 1 is necessary for the stability of this volume law phase. Otherwise, if you measure things and you integrate it out, you can destroy your volume law. And numerically, we find that we get in these dual circuits, we get the same approach to minus 1.25. Okay, so really there seems to be very strong evidence that it's the same non-thermal volume law phase that's obtained either through this kind of dual evolution or through thinking of unitary circuits subject to random measurements. Good. So now let me take 2 minutes to just give you a broader landscape of what's possible, right? So in general, if you're thinking about entanglement dynamics, I've focused on the case where the unitary evolution was chaotic, but as we know, you can get all sorts of different types of behaviors for how entanglement grows in time, ranging from not growing at all in an Anderson localized phase to growing logarithmically in an MBL phase to growing as some kind of sub-ballistic power law in time in a Griffiths phase that may be at the edge of this MBL phase. So you can get all sorts of temporal behaviors of entanglement in time. And now the idea is that if you dualize this, right, and look at the outputs of these dual circuits that come from picking your unitary gates from these types of evolutions, then this temporal behavior maps to the spatial scaling of the steady state entanglement in time for this non-unitary evolution. Okay, so that space-time duality, the leading order behavior is exactly as you would expect. Okay, so if you had log t in MBL, you get log of L tilde in the spatial scaling of these late time steady states. But that's not the whole story. But before I go on, I want to flag related work in Tarun Grover's group, which also which also asked this question of if you have different types of entanglement phases, what happens if you look at their dual evolutions. Okay, so the two things that I want to flag here, one is the existence of this phase where the late time steady state of the entanglement scales as L to the alpha with this power alpha. Okay, so this is indeed intermediate between logarithmic and extensive. It's not just a fractional power. We've done various numerics. Yeah. So, sure.
And now, like whatever we think about MBL, like I think now it's established this log T is an ETH phase. So and it was seen numerically in what's now believed to be ergodic. So in this sense, and of course, even its thermodynamic limit, intermediate time is not going to change. In this sense, log T could be part of actually chaotic story. So in this sense, how does it fit?
Okay, if there is no phase with log T entanglement growth, then
log T is there, right? But it's not in what I'm trying to say. So we already know it's not an indicator, not necessarily indicator of being like MBL or chaotic.
That's okay. If you have a regime of log T entanglement growth, then when you dualize it, you get log L scaling, right? So that's the important part. Yeah. Okay. Okay, good. Right. So it's not just a fractional power; it's also fractal in the sense that it looks self-similar on various scales. What we've also checked is that you can break the dual unitarity, and this fractal phase persists. And then you can actually get a direct transition from a fractally entangled phase to an area law phase instead of area law to volume law. So that's another interesting transition that we could study. Okay, and this fractal scaling doesn't generically occur in unitary dynamics. And then there's already this log correction that I had alluded to earlier, which comes from the fact that it's not just this naive mapping from space to time, but the boundary dissipation gives you these important corrections. In particular, what this tells you is that generically there is no area law phase for the outputs of these circuits. So even Anderson localized systems, which you might expect would dualize to area law phases, give you this log L scaling, and then you get this universal log L scaling for these chaotic circuits, which we've talked about already. Okay. I'm out of time, so I won't go into this, but this is just the statement that, you know, when you have these output circuits, you can prepare them in the lab. Okay, so you start with some input bell pair states, you have unitary evolution, swap gates, all of this is part of your toolkit. You evolve your state, and if you want that output state, all you have to do is act with these post-selected bell measurements at the very last step. Okay, and by doing that, you can get the state that you're interested in, and that's my summary slide, where we used space-time duality as the physically motivated and analytically tractable way to get new types of non-thermal, non-equilibrium states. And more generally, I think a lot is possible when we think of you know, this whole landscape of unitary evolution, ancillas, measurements, and so on. Yeah.
Maybe two short questions. Maybe quick comment is that as far as I remember, the subleading correction was a power law in Ian Fisher's paper, because log L is very easy to understand from the StatMech model without taking the replica limit.
So that's also easily understandable here. It's the difference between quenched versus annealed averages.
I see.
So if you do so we did the annealed average here. If you do the quenched average, then generically, if your circuits are space-time random, you expect volume law, and then you expect a CT to the 1/3 from KPZ. Okay. That'll dualize to L to the 1/3, which is close to what was observed numerically, and then there'll also be an extra log.
Okay.
Yeah.
So, and the other question is, these Griffith phase scaling. So, if you dualize the circuit, what physical process does it correspond to that would give you this power law entropy? What do you have to do physically to get that?
Right. So. Okay. Well, so this is just an example. So, for instance, you know, if you have dual unitary gates and identities, okay, then in the unitary direction, then in the flip direction, you also have unitary evolution plus measurements, which is exactly what you're familiar with. Okay, and then to get the Griffiths phase, what you have to do is you have to build in bottlenecks in the growth of evolution in the time direction, which correspond to layers in time in the dual evolution, where you have lots of measurements. So your measurement rates in the dual direction end up being distributed as power laws in time. That's what you need. You need a broad distribution of P. Like when you're drawing your measurement, you need that distribution to be quite broad.
Why do you need it to be forced? Why do you care which result happens?
What?
Why does it have to be forced? I mean, you can get, can it be not forced?
Yeah, that's right, you can. So that's what I said, that it persists. You know, so we can derive that it happens if it is forced like that, but then we broke dual unitarity and checked all sorts of things, and indeed it persists. So that is this direct transition from area law to fractal. Yeah.
What you understand about this, I guess, the fractal entanglement phase. Is there an understanding of whether that log correction should be there as well?
Yes.
And does it somehow smoothly convert from the log L and MBL or MBL like things that I was just asking about over to this kind of 3/2.
Yeah, so numerically getting the whole phase diagram is actually very challenging because we're doing this kind of subleading stuff. So what we've done is kind of numerically we've done different coarse grain models for each of the different phases. But indeed, I would expect that as you do that, just like your entanglement growth kind of goes from log L to subballistic to ballistic, this would be kind of log L in the leading term to some kind of power law in the leading term with the subleading term evolving as you go through that. Yeah.
Picture, can you also define a local order parameter?
Can I just define?
Can you define a local order parameter in this picture that you have the coherence on the boundary?
Oh,
I mean,
a local order parameter?
Yeah, other than entanglement.
Yeah, so Michael Gullens and David Hughes had some version of this. So what they did is in the setting where you have unitary gates and measurements, right, they coupled in an ancilla spin, and they asked about, whether that ancilla spin, they asked about the purity of that ancilla spin. This was actually also used for experiments in trapped ions to probe this transition. So the question is, how long does it take for this ancilla spin to get disentangled if it's subject to these kinds of evolutions?
Sure, but I guess I'm asking a different question. So okay, it looks like in this dual picture, you don't have to do this post-selection, right? So you're just looking at the density matrix, which is the average density matrix, and you compute the entanglement of this average density matrix. Right. And then you see these log terms. So it looks like that there should be also a local order parameter in this case. And then actually a follow-up question is, if there is indeed a local order parameter, what would be the corresponding thing in the other picture, in the original picture?
Yeah, that's interesting. I have to think. I don't know. I have to think about that. Yeah. I don't know if Matteo Tibor have an answer.
I asked him once.
Yeah, okay. Right. Yeah.
So I would like to, so obviously this parametric reduction of post-selection is very relevant for experiments. So can you comment on what kind of, like how general is this picture? Like what kind of gates are you using? I see, like these are Clifford Gates or?
No, it's completely general. So you can, this is, these different phases I was talking about for fractal versus volume law versus, that comes from what gates you put in there. Okay. So you can put in Clifford Gates, these are swap gates, so you have to have that in your toolkit. Okay. For the teleportation. And then these are this can be whatever you want. I mean, if you want completely
Hamiltonians or any unitary would work.
That's right.
On
that's
that
right.
part of
that's right. So if you want to prepare the volume law phase, these will be scrambling. If you want to prepare the log entangled phase, these will be localized. If you want to prepare the fractal phase, these will be Griffiths-like, yeah. So you can do lots of you have a rich variety of things to play with.
And you have to post-select only at the very end.
You have to post-select only at the very end there.
Okay.
Yeah, that's right.
Thanks.
That's right. Yeah.
Any other questions? If not, let's thank Vedika.